Hi Matt. Really great video on the complex functions and the complex Fibonacci numbers. And I wanted to show you a way of visualizing complex functions that, well, should be way better known than it usually is. And that is by domain coloring. And this really is a rather stunning way of visualizing how the two-dimensional complex plane maps onto itself. And so you can play with this function plotter on this website by Cindy.js. And just wanted to give you a quick overview on how to read these graphs, and then we take a look at what the Binet formula in the complex plane looks like. So actually, let me plot a much simpler function. And I will just, let's start with the identity function. Never mind the red dot. I'll show you in a minute what that is. So this is a visualization of the complex plane, or a coloring of the complex plane. You may be familiar with this, that color means the phase. So the magenta, or well, it's halfway between magenta and red, is the positive real axis, and then as the phase increases, you get red, orange, yellow, green, cyan, blue, magenta. And so this is the phase of the complex number, and the modulus, or the amplitude, is represented with a brightness. So you sort of see within a ring, the larger the modulus, the brighter the dot gets colored. But then, because this kind of representation wants to cover several orders of magnitude of the modulus, because this often happens with functions, they sort of do a turnover at certain multiples. I think it's multiples of e in this example. So if they sort of, at each multiple of e, it loops over from the brightest to the darkest luminosity, and then it starts up again. So this is the function z. Now let's take a look at z squared. We make these things more and more complicated. The squared, squared. And now you see that as we loop through the phases, like a whole turn, the color actually turns twice around the color wheel. And well, this makes sense because, well, the positive real axis gets mapped onto itself, so it retains its sort of magenta color. But then, as you go on the other side to the negative reals, they also get magenta because their square is positive. And then the other half turn loops another time. And well, you can imagine what z cubed looks like. We loop over 3 times in the color wheel as we loop once in the input space. And then you can start making things a bit more interesting. For example, looking at this function. And now this is a complex polynomial with several roots and several distinct roots. So you see that there is a root at 1, the single root, and at 0 there's another root, but that root is double, which you can see that as the colors loop over twice over a single turn around this 0. So the zeros anyway are the points where all the colors meet. And you can get even more fanciful. Look, for example, at add things like this. Now we have, well, the thing is, now we have zeros and poles. And poles also look like all the colors are represented, but they loop around the other way. I think there's one pole at 0 and all the others are zeros, something like that. Anyway, something else you can do. So on this plotter you can't really shift or zoom, but they've implemented a way of making this halfway work. So let's go back to a simpler example, z cubed. And instead of z, let me plot z minus a cubed and now a is actually this red dot as a complex number. So as I move this dot around, I can actually move around my plot and look at the thing, what the function is doing further in the outskirts. And I can also zoom, and for this I have this, they have provided us with this slider E, so I just need to integrate E as a scaling factor into the expression, like so. And now as I move this slider up and down, I can zoom in and out of the function, which is quite really not that interesting for this function. But also, well, as E becomes negative, there's sort of this flip over, which is more of an artifact. And I like to rescale E so that it actually goes from 0 to 1 or something. And I can do this by... And now as I move E, I have this continuous zoom without the flip over. Now let's put in the Binet formula. Let's see. Also, one thing that they permit us to do here is to just type lowercase a instead of z minus a. And what is going on? So this whole thing stands for z. Now we want... Yes, it worked. Whoa! Now, what kind of function is that? Ha 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 ha! It is this really weird shape. Well, it's sort of like a linear function here, like a linear function there. Well, it's not linear. It's the phase is linear, and then the modulus seems to increase exponentially. And then there's really changeover region in between with lots of zeros, and where we can zoom in a little bit, and we can also zoom out a lot. And whoa, what the hell? What is going on here? This is, I mean, you sort of see the kinds of plots that you've had with the real and imaginary part, and this is the whole picture, kind of. I can't really make heads or tails of this, but I mean, it's mighty cool. I mean, the Fibonacci number's got to be in there somewhere, and I mean, the fact that the modulus increases exponentially, yeah, that is what you have in the Binet formula. So sort of these two parts are the different power parts in the Binet formula. How exactly they relate, something like the vectors, but they're not really perpendicular, which I would expect them to be, like the gradient vectors along which the modulus increases. But what is the angle in between? And what is the angle with this line that contains the zeros on either side? And I have no idea. I just leave you with one more thing, Matt, and then you can explore the rest of this. Just you can also change the phase continually as a function of time. And zoom in and zoom out and get high, I suppose. Anyway, I'm going to bed now. Take care.